Finally, I can join the meeting. Okay, my name is Toru Ono from JISF, Japan Iron and Steel Federation. Today, I'd like to talk about JISF long-term vision for climate change mitigation, a challenge towards zero carbon steel. In November 2018, Japan Iron and Steel Federation has launched the long-term vision for climate change mitigation, aiming to realize a zero carbon steel in which hydrogen is a vital measure for carbon-free iron making. The vision is reflected to the Japan's national long-term strategy for climate change mitigation based on the Paris Agreement. I'd like to introduce the outline of this vision, especially focusing on hydrogen use for zero carbon steel making. The preparation policies for the vision are as follows. The scope is after 2030 and until 2100. The boundary is global. The scenario is to aim for consistency with 2 degrees C scenario in IEA ETP 2017. The nature of the vision is to offer a direction towards achieving Paris Agreement long-term goal. The vision consists of 3 parts: future steel demand and supply, long-term climate change mitigation scenarios for steel industry, and JISF's strategy for realizing the scenarios. A forecast of steel demand and supply in the future. According to the UN, world population will keep growing within this century. And there are many people waiting for economic growth. Climate action is one of the SDGs, but at the same time, SDGs contain multiple steel demand drivers to support the population growth and economic growth. We have to reach these inconsistent goals at the same time. But how? Only innovation can give the solution. The steel is the most fundamental and indispensable material for civilized society. And steel stock has a close relation with population and GDP. This is a prediction of stock, demand, and supply of steel in the future. This is population. This is a population, and this is a assumption of steel stock per capita. And gray shadow is steel stock, total steel stock, and red line is primary iron supply, and yellow line is a production from steel scrap. Currently, more than 1.8 billion tons of steel is produced annually on this planet. Considering the increase in the world population and economic growth, steel demand is expected to increase. Steel scrap becomes a larger part of steel resource, but is not sufficient for the demand. And therefore, steel production from iron ore will be still needed even in 2100. To produce steel from iron ore, oxygen is removed from the ore by carbon, and therefore a large amount of CO2 is emitted along with iron production. Long-term climate change mitigation scenarios for steel industry. We had 4 scenarios. The first one is a BAU scenario. only scrap ratio in the iron source increases due to increase in scrap generation, while technical level stays at the current status. And second one is a BAT, a maximum introduction scenario. Maximize the diffusion of the existing advanced energy saving technologies like CDQ, TLT, and so on to the world by 2050. IAETP 2014 assumes that the reduction potential by international diffusion by BAT is 21%. And innovative technologies maximum introduction scenario. The innovative technologies currently being developed like COS50 or HiTeMP will be introduced as a maximum level from 2030 to 2050. And finally, super innovative technologies development scenario. With the introduction of super innovative technologies like hydrogen reduction, CCS, CCU, and so on, that are not yet in place, and the achievement of zero emission of the grid power supply, it is assumed that zero carbon steel will be realized in 2100. And this is a calculation. Upper chart shows CO2 emission intensity, and lower chart is shows total CO2 emissions on each scenarios. Black line is BAU. A rise of the scrap ratio in the iron source lowers CO2 intensity. However, the total amount of CO2 emission will be is increased because of the increase in steel production. Blue line is a BAT scenario. Although the CO2 intensity will be improved compared to the BAU scenario, the total amount of CO2 emission will increase due to the increase in the amount of crude steel production. And green line here is of innovative technology scenario. Assuming innovative technologies can be ready to be in use by 2030 and have been introduced to the world by 2050. The CO2 intensity in the natural resource route will be improved by 10%. And then super innovative technologies, such as hydrogen reduction, CCS, CCU, and zero emission grid power must be provided. Based on the level of technical achievement in 2050, many of pathways can be expected. However, in any case, zero emission from iron making can be achieved by the end of this century. But this is challenging to achieve. 100 billion tons of CO2 is needed to be sequestrated if we realize zero carbon steel only by CCS. And 1.2 trillion cubic meter of hydrogen is needed for 1.2 billion tons of iron making in 2100. There are two main pathways towards carbon-free steel making: carbon use and treatment and carbon avoidance by hydrogen. The first pathway is to keep using carbon as reducing agent and to capture CO2 and store it under the ground, or to use it as carbon resources for valuable metals. Because of keeping blast furnace with coal, the technology is proven, existing, and experienced. Resolution for technical and social issues of CCS and CCU is the key to this pathway. The second pathway is carbon avoidance in iron making by hydrogen. By reducing agent from carbon to hydrogen, only water is emitted in ion making. But this technology is unproven, existing, and inexperienced. Overcoming endothermic reaction may be the biggest challenge. In addition, how to produce and supply a huge amount of carbon-free hydrogen with a rational cost is also a big challenge. Long-term climate change mitigation strategy by JISF. The long-term vision of JISF is divided into 3 steps: cost 50, super cost 50, and hydrogen reduction ion making. Cost 50 and super cost 50 use blast furnace and try to increase the ratio of hydrogen reduction replacing carbon reduction in the blast furnace. And the difference among those projects is a limitation of hydrogen supply. Cost 50 has a limitation of hydrogen supply due to the in-house hydrogen use, but super cost 50 has no limitation of hydrogen because of assumption of hydrogen supply from outside and aims to maximize the hydrogen reduction in the blast furnace. Our ultimate goal is 100% hydrogen reduction ion making, but it will take a long time to overcome many of technical challenges. And considering the existence of a present process infrastructure based on the blast furnace, reducing carbon consumption in blast furnace is an urgent and practical issue. And there are important steps for transition towards zero carbon steel making. For the ultimate hydrogen reduction ion making, we won't use blast furnace anymore. Overcoming the endothermic reaction may be the key. Knowledge from cost 50 project and super cost 50 project will give some very important hints for the issues. Therefore, cost 50 is the first step to the future. And at the same time, massive and stable supply of carbon-free hydrogen with rational cost must be realized as a common social fundamental. This is an outline of cost 50. JISF has been challenging cost 50 project since 2008, targeting a practical application by 2030. This photograph is an experimental blast furnace in Kimitsu Works of Nippon Steel. In 2017, for the first time in the world, we achieved 10% reduction in carbon consumption. The right diagram shows the ratio of reducing reaction in blast furnace. Hydrogen reduction increased from 10% to 20%, and carbon direct reduction decreased from 30% to 20% instead. And in the next step, super cost 50, we will carry to maximize the hydrogen use in blast furnace. This is a very, very rough estimation on volume and the cost of hydrogen for ion making. Assuming a very simple chemical reaction like this, consumption of hydrogen to produce 1 ton of hot metal is estimated 1,000 cubic meters. 1.3 trillion cubic meter of hydrogen is required to replace all carbon reduction agents from present 1.3 billion tons of worldwide primary ion production. And the cost. For keeping cost equivalent as a reducing agent, hydrogen has a linear relationship with coal as shown in the left diagram. Assuming $200 per ton coal, 7.7 cents is the equivalent cost for 1 cubic meter of hydrogen. Australia has a very strong strategy on hydrogen. Now, Japanese steel industry imports coal as a reducing agent from Australia. But in the near future, hydrogen may take the position, especially from South Australia. In conclusion, the challenge towards zero carbon steel presented here is to indicate a direction towards achieving the long-term goal of the Paris Agreement. Technical challenges to achieve zero carbon steel are clear, but very tough. Not only to overcome technical issues in hydrogen reduction I am making, but a huge and stable supply of carbon-free hydrogen with rational cost is essential. Cost-50 is a first step to realize zero carbon steel. Using the technologies gained from cost-50 as a foothold, JISF will challenge super innovative technologies for realizing zero carbon steel. Thank you very much.